My name is Chris Smith. I lead out the consulting services team here at RandSim. My background and experience throughout my career has all been in simulation, and obviously, as she mentioned today, I'm going to be talking to you about engineering energy efficiency, really how you drive ROI through really focused and tailored simulation workflows. For those of you that don't know, Ansys is a software developer. They're part of Synopsys now, who builds out physics-based simulation tools. And so one of the areas where they've really accelerated in is all of these environments where they're taking fundamental equations, fundamental laws, and driving out these simulation environments so you can virtually validate designs and go through that simulation workflow to allow you to predict performance. And that's dominantly within the fluid structures, electromagnetics, and optics areas. And so one of the areas that Ansys has then as a product deployed most dominantly is it's used within design processes and product development space to help reduce time to market and increase product performance. Because they're physics-based simulation tools, they have that grounding in reality. So when you are running these analyses, you know that it is doing prediction based on fundamental laws, and it's not doing any extrapolation or interpretation or expansion of data sets that you often see with neural networks, AI, and other things like that. It's using these fundamental drivers within the physics-based environment to make sure that its predictions are accurate and representative of a reality. And one of the benefits of this is that it really ensures that as you're going through that process and as you're integrating it within a design environment, that you're able to address cause-effect relationships throughout the design process, right? Instead of just going in and trying to optimize for a specific feature and it being a complete black box where you don't know what's happening and it just spits out a result, you're able to actually digest a lot of the information that is being output from the analysis and draft out physical cause-effect relationships that might produce those results. And that can really make sure that, especially for designers on a team that may be using the tools, they're able to start to build an intuition around what those physics drivers are, so you don't always have to rely consistently on this black box simulation tool or something like that providing you data. It's really giving you that real-time interactive experience towards driving value and improvement within the product development space. And obviously, all that is in the backdrop of this ecospace of simulation tools and making sure that you're applying them correctly, right? And so a lot of what I'll be talking about today isn't the above, right? The above is fairly straightforward and well known within simulation tools ecospace. What I'm going to be talking about today is really how you go through an implementation approach, which is critical to maximizing that ROI, right? At the end of the day, as much as I'd like it to be the case, you can't necessarily just give a simulation tool to a brand new engineer fresh out of college who's never done simulation and expect that they're going to definitively be able to drive a return on investment with the tools themselves. But it takes a lot of specialized and tailored focus as you're driving through these workflows, ensuring that you're tackling the appropriate problems to drive that value assessment. And so, while the tools themselves are very straightforward and simple to use and learn to use, the actual implementation of that is really where a lot of the value can be extracted. And so that's what we'll be focusing on today. And I'll start out by going over what the ideal simulation workflow really looks like when applied to a product development space. And so, generally speaking with product development, right, we always start out with those proof of concept evaluations. We want to take a large sweep over the design space. And in simulation, it's very similar. We want to create this analysis that is what I would consider a minimum viable product for what we are trying to represent. So it's as simple as you can get from a simulation perspective to try and take a broad stroke at the entire design landscape. So this could be applied to turbo machinery, power distribution units, data centers, any products within the energy infrastructure industry, to really focus in and get that broad coverage and help identify what driving characteristics are from a physics perspective that move the performance of a system from passing to failing in different scenarios. And in this proof of concept evaluation, right, you're again keeping those simulations very simplistic so you can have that broad space. And that'll help you understand what are the standout design concepts. You might end with just a couple of standout designs as a product of that. Then you can move into the refined design to standards and qualifications. So this is taking some of those standout concepts from the proof of concept section and making sure that these designs match up against what you're hoping for from a qualification of your product performance perspective, or meeting specific design standards or specifications within your industries. And so this is kind of stress testing those proof of concepts, adding in a little bit more detail into the analysis to make sure that you're capturing a lot of the bulk drivers, a lot of those of which are going to be determined in that proof of concept evaluation to understand those characteristics. But again, to really focus in and make sure you've got this product that meets the specs. And then you can go to the next stage, which is that optimize and fine tune these products. And this is something that oftentimes this workflow is deviated from what we see in industry because of time span, right? Somebody might go in and they only have a couple months to bring a product to market. So they skip the first two steps and jump right into optimize. And when you do that, you're robbing yourself of that ability to observe that vast landscape and ensure that your concept you're moving forward with really meets those standards and qualifications. By the time you get to that optimize and fine tune, if you've taken those two prior steps, you can easily add in that extra level of detail to the analysis to make sure it's capturing all of the physics encompassed and all the components within the design, and doing some final incremental sweeps to make sure that you're grabbing out those last bits of efficiency from whatever product you might be developing. Now that kind of bundles up all of the product conceptualization and design phase. We then have two other ways that you can deploy simulation. The first is troubleshooting product issues and failures. So this would be after you've done build and test or after you've deployed this to market, being able to identify and do root cause failure analyses to understand what may have gone wrong and how can we fix that moving forward. And then also for long-term research and development or product development, where you're taking that analysis and you're starting to take that and stress test it against experimental data that you've gathered or field data that you've gathered, allowing you to do some of that validation so that moving forward, as you continue to use simulation for that product environment, that you're able to do so more vastly within just a virtual prototyping environment, not having to draft back or rely on physical testing as much after you've done a lot of that validation. And that's really that kind of after development product support and development that you'd be looking at there. And again, if you follow this workflow through, getting to those latter stages is a fairly straightforward process. But unfortunately, that's not what we see often. A lot of times people try and skip steps or jump ahead in that workflow because they're low on time, they're low on budget, or whatever it may be. And unfortunately, oftentimes that can lead to some detrimental scenarios. And so I'll give an example of a couple years back, we were working with a company who wanted to design a passively cooled power distribution unit. Right, so they've got this large unit that's got bus bars in it, likely for electrical vehicles or something of that sort. And in this concept, they wanted to ensure that it was driven solely through passive cooling. So they came to us with a concept, and they wanted to optimize this concept to grab out additional efficiency points. And what we learned as we started to go through and run some of these analyses is that, unfortunately, they had actually skipped the proof of concept evaluations. We didn't know this at first, but they had come to us with just a single concept, but they really hadn't swept over the design stage or the design space. And when they came into that space with us, they haven't even validated that their proof of concept could meet the standards or design qualifications that they needed to adhere to be able to deploy that solution broadly. And they wanted to jump right into the optimize and fine tune. And the product of that was that after running that first analysis, we quickly realized that this product did not meet those standards and qualifications. There was no way it could stay below the necessary temperatures for a bus bar to survive solely based on passive cooling. It was largely due to restrictions from fluid getting into the bus bar environment itself because of constrictions in the louvers going in. And what that meant is because they had skipped those first two steps, they had lost effectively all the work. They had come to us with a design that was fully scoped out. They had all their suppliers for the necessary parts. Everything was kind of spec'd up, ready to be built, and they were ready to commission their design, only to find out when they were trying to do this quote-unquote fine-tuning and optimization, that in reality, they needed to do proof of concept evaluation and qualification of their design. Now, obviously, there are other steps that were probably skipped internally on their end that led up to this point being at such a failure or a critical point in the design and not seeing success. But realistically speaking, if they were to have deployed simulation in the proof of concept and evaluation phase, they would have been able to vet out that design prospect immediately and understand that if they wanted to do a passive cooling design for this power distribution unit, they probably needed to have a more open environment for their louvers or have it mounted at a higher position so you could draft air from underneath as opposed to be ground mounted. And a lot of other things that they could have started to test out in those coarser simulations that would have led to a large funding save, as opposed to going through that full design process, only have to start back at square one with an unfortunate learning that could have been done so in a much less expensive manner, right? And so really what I'm trying to get at from this is that in this ideal workflow, if you're breaking from it, if you're moving away from it and not following along with it, you definitely increase the risk of wasted time and funds because you're not taking the due diligence and really vetting out each stage in the design process. And a lot of this sounds intuitive and oftentimes is intuitive, but when you're in the heat of the moment in that design review and you got somebody telling you it needs to be done in a month, that's where that creeps in to skip those steps. And oftentimes if you can come back to these fundamentals and really say, okay, we may need to get this done quickly, instead of going right to optimize and fine tune, let's spend that month doing proof of concept evaluation. So by the time we get to the end of the month, we're confident we're going to have a design that'll work. It'll meet our standards and qualifications. And they're just the last few items that need to be fleshed out, as opposed to fleshing out this big design and just hoping that it works at the end of the day. Now, as you're going through this workflow, not only is the exact workflow itself important, following along with these steps to make sure that you're taking these incremental increases in fidelity and detail within the models, but it's also making sure that as you tackle each individual step, you're really focusing on a value-based simulation approach. And the reason that this is so critical, and the reason I use this value-based simulation approach, is that you can go in and you can do a proof of concept evaluation, and you can do it in a manner in simulation where it's really not going to produce a lot of value at the end of the day, right? It might be that you run these analyses and you haven't set up your analysis to really target specific goals within what you need to achieve, right? So for that power distribution unit, the goal was keeping the bus bars below their critical temperature. You could have an engineer that sets up a proof of concept simulation that really doesn't assess that critical design criteria very well. They might start out with doing structural analyses to make sure that it meets seismic specs, right? And that's really breaking from that workflow and breaking from the value-based simulation approach. And so to do this approach, I like to ask myself two questions anytime we start to dive into doing any sort of analysis. The first is, what question do you need to answer with a model? Right? This is getting at, what is the purpose of us running an analysis? What are we trying to understand, right? So for a power distribution unit, it might be, I want to understand what temperature is a bus bar going to get if it's passively cooled as opposed to force cooled. And then the second is, what is the simplest model that can answer that question? And the reason that we take this approach, we ask ourselves these two questions, is it makes sure that we're not going through and just simulating to do simulation and hoping that we'll see what we need to see in the results, right? It helps us really guide ourselves and focus our mind on three key factors, which is first, determining a very specific goal, right? That question of, what do you need to answer? What is the design goal you need to kind of understand as a product of this simulation? Really focus in on finding a very specific goal for an analysis. It's always good to have one specific goal from that analysis. Obviously, we can extract a multitude of information when we're finished with the analysis. But we want to have a primary focus because that really makes sure that we can assess, did we meet or fail against our criteria that we're setting up for ourselves? The second, and this is where that second question really comes into, is just embracing the KISS principle, right? We don't want to create a simulation that answers 100 questions that we're not asking, because that's a lot of detail, wasted time, and wasted compute resource on a lot of information that you don't need at that time. And so it's focusing your simulation, making it as simple as possible to make sure that it's answering those questions, those key principles that you're looking at understanding and assessing. And when you do both of these things together, it really helps you avoid analysis paralysis, right? So you're hitting all three of these markers because you're not going in and trying to investigate 100 things. You don't have this simulation where it has 500 different goals as a product of it. you have one goal, you're making it as simple as possible, and the product of that is there's not a lot for engineers to get hung up on and get into these analysis paralysis traps. As we all know, engineers tend to be very conducive towards getting into, right? Engineers are curious, they like to solve problems. And by designing simulations this way, it not only helps your team develop models and produce results in a more effective manner, but it also makes sure that your engineers are happier, they're more satisfied because they're going to be understanding and driving towards these specific goals and doing so in a segmented manner. And so that's really how you go through that value-based simulation approach. Again, this ties back to that ideal simulation workflow where you can apply these two questions to every single position on that workflow. Within the proof of concept, within the refine on the design and meeting qualifications and standards, and within the optimized fine-tune, and then even after product launch and some of the troubleshooting that may occur or the long-term R&D. Having these two questions at the core of it really helps ensure that the entire time you're going through that workflow, you're maximizing the potential value extraction from the simulation work that you're doing, and you're avoiding a lot of the common pitfalls and traps that simulation engineers can get into, or companies that don't have this driven value-based approach to simulation will have. Now, obviously, a lot of this is good to talk about in principle and in theory, and at the end of the day, it can be a lot harder to actually deploy this solution in reality. And so my recommendation whenever you're trying to deploy this is start out with these two value-based questions, right? If you're a simulation engineer yourself, you're a manager of simulation engineers, write these two things down because that's going to really help make sure that any simulation that is done is refined, it's targeted, and it's specific. Now, getting into the workflow itself, I'm going to give a couple of examples on how you can start to deploy that workflow. A lot of that workflow really is just following the KISS principle, right? Making sure that you're keeping your analyses as simple as possible for your immediate design goal. But I'm going to go through 3 examples here that kind of walk through what exactly that looks like broken down for 3 applications. And so the first one that I have is just gas turbine, right? This is all over energy infrastructure. A lot of power generation is done through gas turbines. And so let's say that we have a primary design goal of designing a new gas turbine from small scale operations. In particular, maybe it's for extracting excess energy off of the exhaust stack of a diesel generator. And so our first approach or our first endeavor should be that proof of concept, right? Wanting to make sure that we're hitting the mark with something that actually meets our design goal. And we're not coming in and just saying like, oh, company A did a turbine that looked like this for this application. We'll just make one that looks similar to that, and then we'll tune on that. No, it's going through first principles. Ansys has tools that actually help guide through this, in particular for turbo machinery. And we could say, hey, we want to design a turbine that can output 5 kilowatts from the waste heat of a diesel generator. We might have a specific temperature, maybe 800, 900 degrees Fahrenheit, and a specific flow rate out of that diesel generator. And we can use some of these 1D tools to help scope out what would a turbine need to look like to extract that much energy, and is it even possible to extract that much energy from a diesel exhaust stack? After that, we might get into, okay, we've got this concept, this design that's passed its preliminary specs, it meets our overall design criteria for that design point. So we might get into refining some of that. So that could be looking at making sure that stresses within the blades that we're designing are satisfactory, and that from a fluid characteristic perspective, we're not having issues. Maybe we don't expect to have as much buildup of soot within the turbine, or we've got some mechanism we're starting to design for cleaning out that diesel exhaust before it moves through our turbine, right? It's starting to get into some of those auxiliary components to design. Now that you have that formative design that meets the criteria, in how it works in those off-design performance areas, and starting to run simulations and evaluate the performance of our system for those conditions. And then lastly, you can follow on with that optimize and fine-tune. We've got our proof of concept done. We've got it refined. It meets the standards and qualifications that we need it to. And now we're going to go in and we're going to tweak the material of the turbine to reduce costs or reduce manufacturing costs by reducing the radius of our rounds or other things like that, right? Then you can get into that fine-tuning. Once you've got those formative elements, as opposed to starting out with a proof of concept where we say, yeah, our turbine has to be all made of this stainless steel alloy, and we need to make sure that it meets this specific standard, and we need to make sure that it meets the seismic standard and all of these other things. instead of going into that proof of concept with this ballooned out environment of criteria we need to make, it's focusing in on the primary goal, finding something that meets the primary goal, and then seeing how you can adapt that system to meet all of those other auxiliary goals. And so these are all workflows that can be deployed within the Ansys ecospace, and they have tools designed specifically for each of these stages, whether it be that proof of concept, those 1D tools, 2D design tools for turbo machinery, getting into some of those refined design standards, or even 3D tools, getting into the optimize and fine tune, and then going past that even to understanding blade flutter or other very complex mechanisms within turbo machinery that are critical to developing an adequate gas turbine at the end of the day. Another example that I've got for that is power distribution units, right? We talked about one prior, but let's say our primary goal is to create a standard power distribution unit that can be deployed in adverse scenarios across the United States, right? We want this to be deployed in Alaska, Florida, Death Valley, you name it, and we want it to be able to withstand all of that and be very standardized. So instead of having that really broad strokes approach, let's boil it down to something simple, right? The biggest issue with power distribution units is thermal consideration. So let's do a proof of concept to design a PDU that can function from negative 40 degrees Celsius to 50 degrees Celsius, covering all of the 50-year high temperatures and 50-year low temperatures that we expect to see across the United States. Once we've worked through that proof of concept, we've come up with some designs, then we can go in and stress test some of those designs over some other standards that we may need to meet, right? So that would be seismic standards, wind safety, hurricane safety, blizzard safety, arc safety, you name it, for a list of regions within the US that we know have really strict and constrained design performance requirements. That might be Death Valley in California, Florida for hurricanes, or Alaska for some of those blizzard conditions. So we can start to kind of grow on our proof of concepts that we developed and flesh out and see which ones are starting to meet the mark across all of these. And then finally, we can get into that fine tuning. Once we have that design, it meets those standards, it passed our proof of concept goals. Now we can try and reduce material costs for the bus bars by pairing out some material, changing out the chassis from stainless steel to aluminum, understanding, do we need a heater embedded in this for all of these scenarios, or can we get away with it only being in there when we're in those Alaska environments and different things like that, right? So it's taking the simulation workflow and applying it as you would any design workflow, starting very simple and growing on an item to make sure that you're not trying to tackle everything all at once, right? If we jumped in right away and we tried to say, hey, we have this concept for a power distribution unit and we want to see if we can change the chassis from stainless steel to aluminum, we've missed 50 questions that we need to answer before we're at that point. And if it doesn't work changing it to aluminum, we might be back at step one because we didn't do a proper assessment in that simulation workflow. And the last case that I'm going to give here is a data center site. So this would be looking at deploying a data center near peak renewable energy sources without any risk for overheating, right? Renewable energy sources are often in the hottest areas in the world, most often in deserts, because a dominant portion of those renewable energy sources is going to be from solar. And so obviously putting a data center in somewhere where it's really hot isn't necessarily the best environment because data centers' biggest issue is cooling. And so what we might do in a scenario like this is say, hey, let's just try and make sure our data center functions at temperatures up to 50 degrees Celsius, right? That 50-year high temperature that we see across the United States. And we can do that through a simple site layout assessment, right? Instead of modeling every little generator and chiller on the site, we can bulk all those up into big volumes and generally just see if we have all these generators producing heat on this site, is any of it going to get drafted into our chillers? Are we going to see any cooling issues as a consequence of that? What's the maximum temperature our coolers need to be able to tolerate for a site to work like this? And after you have some of that precursory information, then you can go in and start to spec the equipment, as opposed to just saying, oh, temperatures don't get above 50 degrees Celsius. I'm just going to assume all of my chillers will be fine as long as they're good up to 50 degrees Celsius. When in reality, every chiller on a data center site re-ingests hot air, right? These things generate heat islands. They have a lot of hot air that is generated, and as a consequence, these sites are above ambient temperature flat out. That is how it is, and that's how it works with these massive sites when you're dissipating that much thermal energy locally. And so as a consequence of doing these preliminary concepts, you might be able to quickly understand and be able to spec out equipment so that by the time you move into that stage for designing the standards, It's no longer a fight with the chiller manufacturer because you need them to get an extra 5 degrees Celsius to cover on it. It's a, hey, I already knew off the bat that these 3 manufacturers are out of the running because they can't produce a chiller with adequate standards for what I need. And I need to move with these 3 chiller companies. Right? And so it really helps set you up for success, implementing that simulation early in that proof of concept stage. That way, moving into those later stages in your project, you can do so with confidence that you have some level of a concept that is going to function for whatever environment or need that you have for it. And then lastly, you can get into some of that fine tuning. Now that you've got that layout, you can potentially move some of those chillers or generators around to save on cabling costs, make it more conducive towards maintenance and accessibility, or other things like that. Having that proof of concept sweep done, you'll have a good idea of what availability you have for motion in that equipment because you'll test out several configurations for that site as an aggregate prior to even getting to that fine tuning. So when you're fine tuning it, you're not running these very detailed analyses over an entire site over 20 different designs. You know that there are really only 3 dominant contenders for what that might be, and you can focus your efforts on those as a consequence. And so that's what a lot of simulation looks like when you're really driving for engineering efficiency and a return on investment. It's taking this ideal workflow and deploying it consistently and making sure that as you're deploying it, you're taking that value-based simulation approach of asking yourself, what question do I need to answer with this analysis, and what is the simplest way that I can do so? And in doing that, you're always going to see a drive for additional success and value extraction from what you're doing because you're not wasting time and you're not having to redo a lot of work because designs failed and they were out of scope for what was really acceptable in that environment. So I'm going to wrap up here, just closing out saying that at Ransom, we have years experience in doing exactly this, in working through these ideal workflows and doing so with that value-based simulation approach. We've done it not only for the energy infrastructure industry, but for other industries across the board, right? And the way that we do that is not only through simulation consulting, right? We're a simulation consulting services provider, and so we do this consulting on our side, but we also sell and provide the Ansys tools necessary to do these analyses, and we provide training to engineers and workflow development for companies to implement these practices internally to themselves if they're looking to try and bring this in as an internal capability, right? And when we go through that process, either in the simulation consulting, the training, or as that tool reseller, we make sure that we own that simulation project or process, meaning that we'll work with you, your engineering team, your providers, whoever it may be, to make sure that you're really maximizing your return on investment from those tools or that work that we're doing with you at any point during that workflow. And lastly, the way that we do this is we try and operate as an extension of your team, right? We don't like to be that black box provider either for the training and tools or for the consulting itself. We like to make sure that you're kept in the loop. That way you're not missing anything during the engagement and you're never sitting there waiting for information. You always have that at your fingertips from our team.